So hello, everyone. We're very happy to have Claudio Gómez-Gonzáles from UC Irvine, and he will speak about the topology of non-degenerate functions of projective spaces.
Yes, thank you. Thank you to the organizers for, oh, did I start too early? Good to go now? Cool, okay. Thank you to the organizers for inviting me. Thank you, Jeremy. This talk is topology of non-degenerate. Oh, wait, what are my footnotes? Make sure you can see those. Topology, and I realize I should also have said arithmetic of non-degenerate functions and between projective spaces. So yeah, before we get going, again, thank you to the organizers. And I just want to make sure people know, like, the hardest thing for me about Zoom talks is the lack of hearing anything from the audience. So unless there's someone like jackhammering behind you, feel free to keep yourself unmuted or, ask questions, things like that. It's just so hard. I'm sure, as we're all aware now, it's so hard to just talk at a blank screen. But anyway, let's go ahead and get started. Oh, actually, before we get started, I'd like to spend just a minute doing a land acknowledgement. The work that I did here was at the University of Chicago. The land where that work was done was ceded in secession 78, following, among many other things, the Northwest Indian War and subsequent forced displacements. So one of the biggest ones being the Treaty of Greenville. It is the homeland. That land is the homeland and traditional territories of the Kiwikapawa, the Piwa-Riwa, the Anishinaabe, the Miamiakia, the Kaskaam, and the Ochtisakawan, the various groups of people. And I have one quote that I thought was relevant from the time. This is at the signing of the Treaty of Chicago in 1821 by Anishinaabe Chief Matea. And the quote, he said many things, but the quote that I thought was, one that would be good to snatch was, our country was then very large, but it has dwindled away to a small spot, and you wish to purchase that. So, all right, acknowledgements. Let's go ahead and jump into the talk. So I will begin with a quick commercial for some of the main results. So one of the big theorems that it was the most surprising to me when I was doing this work is the statement. We have these, oh wait, how do I gotta get my pen going? There we go. Okay, cool. So the talk concerns the talk concerns maps between varieties. So in this case, we're looking at maps from CP1 to CPN, and we're looking at algebraic morphisms, meaning maps given by polynomials. And one of the main theorems is that the inclusion of most degenerate functions, which I'll talk more about what that means, but it's somehow polynomials that in some sense are the most degenerate. They fill up the least amount of CPN. These polynomial maps, the inclusion of them into the space of all maps from CP1 to CPN of a fixed degree is a rational homotopy equivalence. Somehow all the data, all the rational homological data of these spaces is contained in the spaces of most degenerate functions, the functions that take up the least amount of space in CPN. And I'll talk more about this. We'll sort of introduce what this means, what this product is, how it works. Or this is the main result. It's or one of the main results that this inclusion of most degenerate functions gives us a rational homotopy equivalence. Some other big results. So first off, we have this theorem of Milgram from 1997, which regards spaces of maps from CP1 to CP1 of a fixed degree D, where he looks at the action of PGL2, the automorphisms on the target. So this is an action by post-composition. And he shows that this space, he shows a lot of things, that the space is isomorphic to a space of Toeplitz matrices, and among other things shows that this space is Q acyclic. Let's see what else. We've got a theorem by Claudio Salvatore in 2006. Go ahead.
How hard is that to see from Siegel's result? Because Siegel's result implies that degree 1 maps and higher degree maps have the same rational homotopy type.
Yes. So were you asking about Milgram's result or yeah. this one?
I was thinking Milgram.
Because actually, Oh, go ahead. I'm sorry. Go ahead.
Yeah, I was just saying, is the Milgram result like mostly? I mean, it doesn't seem like immediately obvious from Siegel, but it's like
Right.
you're taking a space
But you
mod
can,
and other spaces that are have the same rational,
absolutely, yeah.
or like a different
Yeah.
map of homotopy equivalence between them. So plausibly this other thing is too, or something.
Yes, I mean, so secretly, I mean, I'm being a bit cheeky here. Like, this is really like three shadows of the same theorem. And the third one, so this one is, I guess I'll speak to what you're saying really quickly, Jeremy, which is like, if you notice, and this is sort of a shadow of Siegel's result, right? Is that this is, I'm looking at the homology of degree D algebraic maps, rational maps from CP1 to CPN. And the rational homology, as you notice, has nothing to do with the degree. And this is not based maps. This is a little different from Siegel. We'll talk about Siegel. I'm going to sort of spend a little time reviewing this, but it has nothing to do with the degree, which is sort of like an interesting, like, okay, maybe something's going on here. And the last result that I'll mention is one by Farr-Wolfson. This is in 2015. It's fairly recent. And other people have, they proved other things. Other people have like come up with this count in other ways, but like the spirit in which I'm bringing it in here comes from their paper. And this is really three shadows of the same theorem. So this last statement is a statement about point counts. It's about like saying, okay, well, we have these equations that tell us about maps from P1 to Pn of degree D, and we can, these equations are defined over the integers, so we can ask about point counts. We can like ask, we can reduce mod P and ask how many solutions there are. And it turns out that like all three of these statements are like all shadows of something else. Like they all come from a deeper theory. They're like a part of a deeper series of results. And this is supposed to be a commercial for mean results from my talk, from my own research. So you're like, well, these are all by other people, Claudio. Like, where's your result? So mine is extending a lot of this stuff, partial analogs of these theorems for maps that are based in CPM, where m is greater than 1, which has like historically been sort of difficult. And I'll talk about why that's a different thing. Does that like, I promise I'll get more to it, Jeremy, but does that like assuage you for now?
Yeah, I'm aware Siegel didn't write down this statement, and Milgram did, and all I was saying was like maybe a lot of the work is due to Siegel.
Yes, yeah. I mean, Milgram like also did it in a new way by sort of like coming up with a new way to interpret these things using these Toeplitz matrices. But like, yeah, the QA cyclic part of the result is definitely like largely. I mean, you could come up with it due to. Oh,
May
go
I
ahead.
make a comment here?
Yes.
So am I right that I mean Siegel's result is stable, but Milgram's result is QA cyclic in all degrees?
Yes. So I'm going to move ahead, and we'll because we're going to hit all that stuff. So this is I don't want to jump ahead into like the middle of the talk, but
yeah. So, but I was saying, well, but like the base point doesn't super matter because you can compare different components by composing with various degree maps, and like there's no rational homology in high degrees. So like once you get to 1, whatever. I'll let you give your talk.
Right. No, it's perfect because this is like, it's like you've seen my slides. This is great. So let's jump ahead a little bit. I do want to talk about Siegel stuff. This is where the story begins.
Ignore whatever I'm saying. Like I can talk to you afterwards also.
Okay. Yeah. But it's good. I mean, this is part of the spirit of all this. So I guess the thing that I'll mention is like some of the main tools. Like there's a lot of interplays here between geometry, topology, and arithmetic. I'm only mentioning a couple of them here. But the thing we're going to be doing is looking at non-degenerate maps, and in doing that, we'll be looking at maps that like fill up only they're sort of ranked by degeneracy. We can look at maps from CPM to CPN that fill up a particular amount of CPN in some precise sense. We'll be able to come up with I mean, there's a spectral sequence that like computes the homology of, or the cohomology of like the actual space, maps from CPM to CPN in terms of these non-degenerate maps. Or these spaces of non-degenerate maps, and we'll also see arithmetic and how it sort of plays into this whole story. So let's jump into like what everyone is already like. I mean, everyone feels this. This, of course, the story has to begin here. So this is actually right before Siegel. This motivates sort of what Siegel was looking at, which is there was this paper by Ilse and Wood that looks at like energy functions, and in particular, like if you look at the example on the sphere, with the standard Riemannian structure. This energy function has no critical points except for the set of rational maps, where rational here means, ratios of polynomials. One of them has to be degree D, the other is degree D or less, and they have no common root, right? We can think of these as maps from CP1 to CP1, or you know, you can think of it as the Riemann sphere, however you want to think of it, right? Like this is sending points from C to C, and we can also add in this point at infinity with no problem. And this is like what motivated Siegel to originally start looking at these, you know, this statement that like the harmonic maps are the rational maps, is what leads Siegel to this original like theorem. This was in 1979, where he shows that the inclusion of rational maps, you know, these degree D rational maps into the space of continuous maps of degree D, where degree here is, oh, you're not seeing my footnotes for some reason. That's a bit annoying. Well, whatever they're there, I'll scroll a little bit. But the degree here is defined in terms of Kähler classes for continuous maps. So Siegel proves that this inclusion is a homotopy equivalence up to the dimension D, right? And the way he did it, as people have already said, like, you know, okay, there's like a base point, there's maybe not a base point. Siegel did it by I'll have this, I mean, I literally called this quick aside on base points. Oh, I'm sorry. There's also a statement about maps from CP1 to CPN. It's the same result, but the range changes slightly. So let's talk a bit about base points. So Siegel proved this result by looking at based maps, right? So when we impose a based condition, in particular, the condition he imposed was infinity goes to 1, right? So when you do that, like you can think of these configuration spaces, or I'm sorry, you can think of these spaces of maps as configuration spaces, as configuration spaces of roots and poles. So as an example, I have like a picture of a point in RAT4, right? Like this is a degree 4 map from CP1 to CP1, and the poles are colored in red, and the roots are colored in red, and the poles are colored in blue. And the only rule here is that like the poles and the roots cannot touch, right? For the degree to be well defined, we have to keep the poles and the roots away from each other. So in a more modern language, and this is like relevant, this is language introduced by Farbolson in 2015. We can like generalize this idea to these spaces they call poly-DMK, where you have m tuples of polynomials. They're all monic, they're all degree D, and they have no common root of multiplicity greater than or equal to k. So with this language, the stuff we care about, like this space of rational maps, is, you know, the multiplicity is 1. We need n+1 polynomials to get a map from CP1 to CPN, and of course the common degree is D. They're all monic. So these are based maps, right? And yeah, again, here you have like the number of distinct colors. If you want to think of them this way, they're just configuration spaces. And you have a number of distinct colors, a number of points of each color, and then a maximum incidence degree of all the colors, right? So this is like really useful in connecting some of the theory of like braids to the theory of rational maps. That's a whole other story I won't get into. It's a really interesting story, but not for this talk. And it's a really good paper. I do recommend people. It's like the topology and arithmetic of discriminants, I think is what it's called, or no, resultants. And then it's, I think, the first paper in that series. I'm not just saying that because Benson's my advisor and Jesse is my current, postdoc advisor. But it's a really good paper. So as people have noted, it doesn't really matter if we look at base maps or not. Like we're going to get the result either way if we prove it for one or the other, because like there's this compatible fiber bundle. So, you know, if we can prove that like these maps are isomorphisms in the range we want, like we'll get that these are isomorphisms in the range we want, and vice versa. So Siegel's proof, the way it works, and this is important sort of for appreciating why this problem gets harder as the degree or as the dimension of the domain grows. What Siegel's doing is he's looking at spaces of divisors. He's saying like, well, our roots and our poles are like all of these isolated points. We can look at configurations of them. And he builds these non-algebraic stabilization maps. So the basic idea is like you've got your roots and your poles. You can contract C to like say the unit disk and pull all of your roots and poles in, and then add a new root and a new pole, you know, just outside of that disk. And it gives us a nice map from rat D to rat D plus 1. Oops, that's the plus 1 is in the wrong place. Oops, sorry about that. That should be plus 1. Sorry about that. And he builds these stabilization maps, and he also has this limiting space where he's able to like establish a homotopy equivalence between this space and a space of continuous maps. Of course, like you also have to prove that these maps are like preserving homological data in the spaces that you want them to, or the ranges that you want them to. And that's how the ultimate proof works. So you can imagine this is like more difficult if your divisors can have more form, right? Like your divisors here, your roots and your poles are just points, and you have control over how many points there are. But as things change, it gets more difficult. As the domain grows in size, this gets much more difficult. But anyway, like this was a great result, and it like uncovered a more general sort of story and a more general sort of phenomenon that people really jumped onto. So I have here just like a mention of a few of the generalizations. So like Kirwan has a great paper. It's a really good paper on genus G surfaces in the Grassmannians. So it's a similar result where like the algebraic maps, the inclusion of algebraic maps into the space of continuous maps gives us like, homology equivalences in a particular range. We have a paper by Guest where we look into maps into toric varieties. We have one by Guest, Kozlowski, and Yamaguchi, which is like on these particular like symmetric products, which in the language of Farb-Wolfson is poly DM1. What else? We've got, that's right, we've got a great one by Boyer, Hurtubise, and Milgram, which is like maybe a bit more complicated, but again, it's CP1 into something, right? Like in this case, it's a smooth, compact Kähler manifold with like a nice group action. And then we've got another one this is a more recent one by Kozlowski and Yamaguchi on the spaces that Farb and Wolfson introduced, the poly DMN K spaces. Again, like uniting all this like phenomenon where we have these like finite dimensional, often just like things that we can phrase as configuration spaces, and they are approximations of these like larger spaces of maps. Okay, cool. So there's many more, but notice, as I said before, that like the dimension of the domain, at least in the space, at least maybe more generally the domain of like, or the problems, sorry, the dimension of the domain where we're thinking about spaces of maps, or sort of more generally like the things that we're doing configurations of are usually 0-dimensional, 1 - 1. This is like sort of the only case that was like well studied for a long time. There's a quote by, it's literally in Siegel's first paper where he like says the case of PM, meaning maps from PM to other varieties, when M is greater than 1 is more problematical. Very like appropriate quote. So I'd like to just call attention, like the whole theme of this program is like very reminiscent of like another highly advanced, I mean, it would not surprise me if no one here has heard of it, like a very highly advanced result called the Stone-Weierstrass theorem. That was supposed to be a joke, but no one can laugh, and maybe it wasn't that funny, but like, Zoom makes things tough. This is maybe the version of the Stone-Weierstrass theorem that you would hear in, what is it, like, I think math 3100 for you all, in an intro to analysis class, where you have a statement about like a continuous map being well approximated by a polynomial up to epsilon, like uniformly approximated up to epsilon. In a more modern language, we have statements about like subalgebras of continuous maps on say like a compact Hausdorff space. And we have density statements like, this is a really particular nice formulation. This is the version that I think is most relevant to what we're talking about. The idea here is like, we want polynomials to approximate continuous maps. And like, when someone says that, like the first theorem that pops into my brain is always Stone-Weierstrass. And we can actually take this seriously in light of another important result, which is like, and this one I think is just sort of one of these results that people know and don't always write down, which is like, if we have maps from a compact Riemannian manifold into some space, there always exists some epsilon such that if two maps are uniformly epsilon close, then they must be homotopic, right? Like maps that are sufficiently close must be homotopic to each other. And this is like, okay, this actually seems like a reasonable recipe. Like if we can take the Stone-Weierstrass theorem and apply this additional result, it seems like we can get statements about, I guess in this case, it would be like surjectivity of maps of homotopy groups between spaces of polynomials and spaces of continuous maps. Particularly like if you can build your approximations in a way that like respects, in this case, I said homotopy groups, like so maps from spheres into your space, or products with spheres. So, okay, like this is great. Like how can we use this to attack spaces? And this was like, honestly, like when I was first hearing some of these problems and sort of understanding what people were thinking about, I was like, this is so great. Like we can use these ideas to attack morphisms from CPM to CPN, right? Like we're getting away from this idea of controlling things using divisors, and we're using this other result, this like Stone-Weierstrass type result, to try to generalize what we're doing. Unfortunately, I was born too late, and someone else got to it first. Jacob Mostovoy. And this quote, just a little caveat, may not be attributable to Jacob Mostovoy. It might be more attributable to me when I read his paper, which is like, oh, all of this work can be framed in terms of Stone-Weierstrass. So let me just sort of outline really quickly what he's doing, where he says, okay, like this is sort of spread out between two papers in 2006 and 2012, which is that if we're looking at maps from CPM to CPN where m is greater than 1, he comes up with exactly a Siegel type result, which is like the inclusion of holomorphic maps into the space of continuous maps induces isomorphisms in a range. That range grows with the degree d. And the space here in question is like, you know, to make this make sense, these are homogeneous polynomials and m+1 variables with no common root. And his proof sketch, I mean, truly his proof sketch is just use Stone-Weierstrass. I mean, like, it's a really great paper. The ideas are really cool. And I mean, I'm being a bit like cheeky again, like it's used Stone-Weierstrass, but also like you have to do this result of like analyzing, you have to like introduce stabilization maps, and that's a bit more tricky because you're not doing it in terms of divisors. You can't control things the way that you do with you know, maps from CP1 to CPN. But regardless, like you use Stone-Weierstrass to do the work at the end, where you build this limiting space and you want to show that it's like homotopy equivalent to the space of continuous maps. And that's like the real secret sauce. Yeah, so ultimately, like what he's doing is he looks at spaces of maps that restrict. So instead of using the based condition, he's using like the fibration, or in the holomorphic category, it's like a stratified map that he's looking at is a restriction map. So you have maps from CPM to CPN, you restrict to some CPM -1 and look at those maps. And your fibers are given by these spaces, which I call morph F. So like there's spaces of maps that restrict to a particular map on a particular CPM -1. And he gave an inclusion into a loop space, into a space of continuous maps. And again, he like establishes a homology equivalence in a desired range. And I'd like to remark that just like in the m=1 case, and just like what other people have been mentioning so far, like the right-hand side, this thing, like the limiting object, it's invariant with respect to D. Like its homology is like something that exists independent of the degree. So to sort of sum up, and I think to again address what people have brought up so far. Oh, go ahead.
Reason to write it the way you did as opposed to just a component of the loop space? Like, is there any natural?
This bit?
Yeah,
yeah. Oh, go ahead.
That connected components of H spaces are all homotopy equivalent.
Yeah. This is like mostly for my own, like, yeah, okay, that's a good point. Like everyone should like sort of know these like these homotopy components are all equivalent. This was like honestly something that was just useful for me when I was writing down all this stuff, because it was like I was easier able to like compute the groups that I wanted. But you're right, like there's no particular reason for doing that. Like this is the actual map that we care about. And as you like observed, like the components are all homotopy equivalent. So just to sum up really quickly, like the story on homology is that for Siegel in 1979, we had this inclusion from maps from CP1 to CPN. The inclusion from rational maps into continuous maps is a homotopy equivalence in a particular range growing with D. Mostovoy adds to that story in 2012, looking at maps from CPM to CPN. Again, looking at the inclusion from holomorphic maps into continuous maps, and he gets a homology equivalence in a larger, or I guess in a range that is again growing with a degree D. And it just generalized nicely. There's like this -2 is like a sort of an artifact of the violence of truncated resolutions, but like this piece and this piece, I mean, this like nicely generalizes that piece. So this is the story, and the rational story. And by the way, my results are sort of coming up sparsely here and there inside this, but like the real meat of what's going to come up, like sort of piecing things together, but the real meat is going to come up in a second. The rational story, which is relevant for the point counting for these other sorts of stories that I'm trying to tell, is that the cohomology of maps from CP1 to CPN is independent of degree D. And moreover, like we have these isomorphisms where these two things are isomorphic because of Siegel, and these two things are isomorphic due to, this is something I mentioned at the beginning of the Caddox-Hillel paper. Now, these isomorphisms, oh, go ahead.
Isn't it like clear, or couldn't you just use Siegel? So Siegel says that the space of continuous maps, or the space of holomorphic maps approximates the space of continuous maps. Then you just need to compare connected components of continuous maps. And normally you can't do that because like they're unbased, so you can't stabilize.
Right.
But you know, you're just interested in rational stuff. So you're looking at like maps into CPM or something. Well, you might as well look into CPM localized at Q, right? That doesn't affect anything. And then now, you know, there are homotopy equivalences of CPM localized at Q of fractional degrees. And you could just compose those to go between components. So like you don't need to calculate to know that the components should be equal. And you can't compare 0 to those because 0's, you know, not a unit. But
yes, I think and I guess the point here is not necessarily that these things are like sort of abstractly isomorphic. I was going to like mention there's a particular like map that induces this isomorphism.
yeah, and that's,
but I would like, oh, go ahead.
So, or you're saying like raise something to the dth power. And I
Right.
guess what I was saying was on the continuous side, probably that has an inverse.
Right. I see what you're saying.
You're applying something to the holomorphic side that's not an automorphism. But if you think about it like in the like Sullivan,
Yes.
Quillen localizing spaces world, it should be maybe clear on the continuous side that this has a inverse, and then Siegel,
Yes.
continuous and holomorphic are the same in a
Right. So yeah, and that's absolutely like what's going on here. Like often what like, and that's what a lot of my like the sort of nitty gritty details of a lot of my own proofs are like do things in the continuous side, and then we can use these stability things to sort of pull them back over in ways that make sense. But yeah, that's absolutely true. So let's jump to like the slightly higher degree story. We'll sort of see where that goes. So or the the higher codomain or higher domain dimension story. We'll see where that goes. So regardless, like the isomorphisms here are all induced. First off, this one is just induced via inclusion, but this one is induced, as you're saying, Jeremy, is coming from this map where we're precomposing by z to the d, right? We're like just taking our linear maps and just putting a z to the d in them. We can also, and I guess this is the thing I was mentioning at the beginning, like this is all sort of like a shadow of something grander. This homological stability is connected to number theory via this point count. So this question of like, what does topology have to do with arithmetic is one that I'm going to like do a quick overview of very quickly. And then we'll come back to addressing these spaces of maps. So I would like to do a quick like topologist overview of a working topologist view of étale cohomology, which is that if we have a variety defined over the integers, we can extend scalars, right? Like we can either extend scalars the way we normally do, where we think of it over the complex numbers, we have a complex variety, or we can reduce mod p to obtain a variety over fq bar, right? So, or fp bar, I guess in this case. So from there, we can associate the usual sort of singular cohomology that we're all used to our complex points, or we can associate this is the étale cohomology that was introduced by Grothendieck and Deligne to solve the Weil conjectures, the Weil conjectures, the basic details here is that in particular, especially when y is smooth, we can establish isomorphisms between these spaces, at least like their dimensions. I'm sorry, between these cohomologies. So this is like a connection between, I mean, it's not quite there yet, but this is a connection between the complex points, these varieties that we're studying, or these topological spaces that we're studying, and these varieties regarded over finite fields and their algebraic closures. So Hasse has this fundamental observation that like we have this map Frobenius that like picks out the FQ points from the FQ bar points of a variety over FQ. And if you take this very seriously with the étale cohomology, you get the Grothendieck-Lefschetz fixed point theorem. This is sort of the main tool we're going to use. You get a formula using the traces of Frobenius acting on cohomology that allow us to count the number of solutions to a particular equation over FQ. So this is like the fundamental object that we're using. This together with like comparison theorems is what like connects these worlds of topology and arithmetic. Here, like the eigenvalues of Frobenius that we're summing over these traces, these are called weights. And you can get these equations that take these weights and associate to them point counts. So this is like, this is really powerful. This is like only a little bit of a little taste of this story, but the way that it shows up here is that when Frobenius the action of Frobenius is particularly nice, there's all these words like Tate type, you know, but essentially like the cases that we care about here is when the action is acting in a very particular way by some power of Q. One can literally compare the Poincare series of a space with a number of solutions to those, if we take the equations that created that space and regard them over FQ, we can literally compare the Poincare series of the space to the number of solutions to the equations. So like one of the most straightforward examples is like the equation, or like rather the inequality x doesn't equal 0, right? So over FQ, you're like, how many solutions are there, or how many x are there that satisfy this equation? X does not equal 0, and it's easy, there's q minus one of them. But like the connection is that this can be this can be framed in terms of the Poincare polynomial of the punctured plane or the circle, namely that q minus 1 is equal to q times what 1 minus, or q times 1 minus q inverse, right? So this is again only like a shadow of a theory that is like very deep, but the way we see it now is that in this count of Farr-Wolfson, where we're looking at the number of based maps from CP or from P1 to Pn of degree D over FQ, we can see the homological stability in this statement, and it's coming from right here. Like this little piece is telling me that there's some homological stability afoot. I think I said that on the next slide. Of course, like the point count depends on the degree simply for like dimension reasons, but like the actual meat of the count, like the actual tough stuff on the count, doesn't depend on the degree D, and this is what has to do with this homological stability that's happening with spaces of rational maps. So bringing this all together, the story for m greater than 1 is that the cohomology of maps from CPM to CPN is also independent of the degree D. And again, we have these isomorphisms from like the degree 1 algebraic maps, aka like these are just spaces of matrices, to the degree D maps from CPM, the degree D continuous maps from CPM to CPN. We have this rational equivalence. This isomorphism is induced, like we can sort of see it by composing again with this map that looks like taking z to the d. I mean, we're sort of taking every piece and every coordinate and raising to the dth power, and then followed with inclusion, right? So this isomorphism comes through this composition where we first go from degree 1 algebraic maps to degree D algebraic maps, and then include into degree D continuous maps. So it's similar to the degree 1 story, but it's like in this picture, you can see that it's slightly different. I'm sorry, the dimension 1 story, the m equals 1 story. But as you can see, this picture, it's like slightly different. So in the d equals 1, I'm sorry, the m equals 1 case, this is the case of rational maps. Every map here is a rational homotopy equivalence, right? Like the map from rat 1 to rat D is a rational homotopy equivalence. This is the precomposing with z to the d map, as is the inclusion into the space of continuous maps. And that's why all the point counts work out to be so nice. In the m greater than 1 story, we certainly have that this composition is a rational homotopy equivalence, but like it's less clear what's happening with these maps. And this is some of the stuff that I'm trying to answer with what we're doing in this talk. So yeah, I guess just to sort of say it more explicitly, this question is like, are all these maps homotopy equivalences, and how do we see these things in the point counts? Sorry, I've lost my place in my own notes. So the basic idea of the approach that we're going to outline here is that we're taking advantage of the homogeneous structure of CPN. So in particular, like the most basic case, the D equals 1 case, and I actually mean that this time, the D equals 1 case is simply about matrices. And in the D equals 1 case, we have, I mean, Graham-Schmidt just gives us like a nice equivalence of bundles. This is just like projective Stiefel manifolds, you know, like m+1 frames in C to the n+1. And there's a nice inclusion that like gives us, you know, this like nice equivalent. I mean, this is just a homotopy equivalence and allows us to compute this stuff right on the nose. So understanding how the images of these maps lie in PN just tells us the whole story. And the goal is to sort of generalize this to higher degree, or at least sort of see what's happening with higher degree. So can we, like, using the data of where these maps end up, where the images of these maps end up, can we start to like pick apart these spaces and analyze them a bit more carefully? So to do that, we introduce these spaces. I don't have a good like way to say these spaces out loud, but like these are the spaces of maps whose image fills up some subspace of degree less than or equal to dimension R in CPN. So we have maps from CPM to CPN, and we want to look only at the maps whose like the projective span of their image is contained in an R plane, or like, you know, some R plane, not like a fixed R plane. Right, so this is like a nice, like, this is going to give us a filtration of the space of maps from CPM to CPN. And this is like an equivalent way that was helpful to me when I first thought of it. This is like, we can think of this space as coming from a map from the space of maps across the Grassmannians, where we just look at like the maps that are, you know, annihilated by the equations defining the Grassmannian. So the whole point here is we're filtering by degeneracy. If we look at the strata of this filtration, then we're going to get these spaces. I call them R, you know, spaces of map CPM to CPN degree D, that have maps whose image is filling up an R plane, right? Like some R plane in CPN. So we can index these maps sort of by degeneracy, right? Or I guess it's sort of co-degeneracy in this case. So, you know, this space, this R here, is telling me I'm looking at maps that fill up a CPR rather than all of CPN. Okay, so the basic theorem is that this stuff is like nice enough to give us a spectral sequence. The actual like work of making this filtration sort of does everything we would want it to, and we get a spectral sequence with E1 terms given by the cohomology of these strata, these like R degenerate pieces. That's not so surprising. That's like, you know, just some sort of quick checks, or you know, they weren't quick when I did them, but you know, some sort of like nitty-gritty little checks to make sure everything works out. But what we can do more than that is we can introduce this case when n equals R, right? So this is like the space of maps from CPM to CPR such that the map is contained in no hyperplane, i.e. the map is non-degenerate, right? So this particular case of maps that are non-degenerate come from this fiber bundle where we look at the maps that fill up some PR in PN, and we project down to that PR. This space is going to come up as the fiber of that bundle, right? Namely like the non-degenerate maps, right? So this gives us like a whole different way to sort of pick apart these spaces of maps from degree D from PM to PN. And the sort of summary is that we can rewrite that spectral sequence using this sort of nice form, this twisted product in terms of non-degenerate maps. So you want to look at spaces of maps from CPM to CPN. That's easy. Let's just look at all the R between M and N, and we'll take the non-degenerate maps and sort of twist them in just the right way to make them fill up all of CPN using the automorphisms of CPN, right? Here, H is like a stabilizer of some fixed CPR and CPN. Cool. So let's ask this basic question. If we want to compute the cohomologies that we care about in terms of these spaces of non-degenerate maps, well, okay, what can we say about these spaces of non-degenerate maps? The first thing that we'll say is pretty easy, namely that if the dimension of the space CPR is less than the dimension of CPM, well, then there's just no maps at all. So of course, like there's no non-degenerate maps. That one's very easy, right? Slightly less easy, I mean, still very easy, is that if m equals r, then every map is non-degenerate, right? Like, of course, if you're having a map from CPM to CPM, it's not going to land in some hyperplane. Okay, these are the sort of trivial cases, but slightly less trivial is we have a Zariski open embedding, right? If we quotient by the automorphisms in the target, we have a Zariski open embedding into a space of Grassmannians, right? We're just looking at all the degree D monomials and n+1 variables. This allows us to do things like calculate dimension, but it also tells us that like the space of degree D maps will be empty if the target is sufficiently large, right? And it controls that in a nice way, right? Like if you have a map from, if you have a degree D map from CP1 to CP infinity, like you can't possibly, I'm sorry, not infinity, but like CP a million, you can't possibly hope that it will fill everything up, right? Like there is some sort of way to write down nicely like how big you need your degree and your domain to be in order to actually have a chance of having non-degenerate maps. Also, there's a nice story for that edge case, which is called the Veronese map, right? Like if we want to look at maps from CPM to CP m plus d choose d minus 1, right? Like this is just given by the Veronese map, right? Which is like the unique irreducible non-degenerate hypersurface of CP m plus d chooses d minus 1 up to automorphism. So this gives us like a nice form for these spaces of degenerate maps. Namely, they're just given by the automorphisms of that projective space. Moreover, this like is sort of nice enough that like this this tells us, and I know this notation is quite a lot, so let's just like sort of pick this apart. If the degree of the target is sufficiently large compared to like the domain, the dimension of the domain and the degree of the map, then we can't have non-degenerate maps, but we can have least degenerate maps, and they're given in terms of this, like you can parameterize them in terms of this projective Stiefel manifold. So just to summarize it again, like if the target is sufficiently large in dimension, then we don't have non-degenerate maps, but we do have these like spaces of least degenerate maps. Okay, so what does all this mean? So if we want to look at the actual topology of these things, remember like the whole point of this stuff is that the PGL action on maps into CPN like respects these degeneracies. And like the maps that we mentioned earlier, these maps inducing these isomorphisms that I mean, Jeremy, like you mentioned in the sense of like the Quillen, you know, whatever, all this like sort of localizing, all these maps are going to factor through these least degenerate spaces, right? So let's just outline the m=1 case, which is like, so we have rat1, the degree 1 maps, which is just the space of matrices. We have rat-D, which is, you know, sort of what we're used to. And we can introduce this subspace of most degenerate maps, right? These are like the maps from CP1 to CPN of degree D who only land in a P1. Like they don't take up any more space inside PN. Well, remember, like this map is a rational equivalence. This map from PGL2 to rat-D, as we've observed like several times, it's just precomposing with zeta d, it's going to be a rational equivalence. And this map is a rational equivalence. So like the fact that this one is rational equivalence tells us that this one's a rational equivalence. The fact that this one is rational equivalence and that this one's a rational equivalence is going to tell us that this one's a rational equivalence, right? So this immediately tells us that like the space of most degenerate maps has all the homological data contained in it of these spaces of all rational maps. And more generally, if we try to frame this in terms of maps from CPM to CPN, because we're using things like truncated resolutions to get at the homology, the cohomology of these spaces, we don't get the exact same result. We don't get that this map is a actual equivalence, but we do get that it's an equivalence in some particular range, like a rational equivalence in some particular range. So to sort of summarize that, yeah, that's what I just said, we're using truncated resolutions. To summarize, this leads to these two theorems, which is that the first one is the m=1 case, which I've already said. The most degenerate maps have all the rational homological data of all the degree D maps from CP1 to CPN. This was the commercial at the start of the talk, but we can also try to generalize this to maps from CPM to CPN, where we grow the dimension of the domain. But rather than an outright isomorphism, we just have an isomorphism in some particular range. In this case, less than D, up to D-1. This also gives us an immediate sort of extension of what we mentioned earlier from Milgram's result, which is that oh, sorry, I didn't finish this one, which is that this is just reminding you that the most degenerate maps are these ones that we can build in this nice way using this twisted product. But regardless, the extension of Milgram's result is that if we look at the post-composition action, which gives us a map from PGL into the greedy morphisms, we get isomorphisms in rational homology up to, again, this degree D-1. So when we take quotients, we're going to get a statement about homology groups being 0 in that range, right? So we don't quite generalize Milgram. I don't tell you that this quotient is going to be QA cyclic, but we can at least control its homology in some particular range. Okay, so the last few things I'll say, because we are running a bit low on time, the last few things I'll say is just some alternative ways that this filtration, this sort of way of studying spaces of maps, it changes the way that we have access to some particular limiting statements. So remember, if n is sufficiently large, our filtration stops, right? Before we somehow don't get any more when we're well, in this particular case, we have a space of least degenerate maps. We don't have any non-degenerate maps, but we have spaces of least degenerate maps. So in that particular case, we have this top stratum, right, which is given its homology is very nice. It has this type of a it has this homotopy type of a projective Stiefel manifold, and that gives us a theorem, which is that if the degree n is, or if the dimension n is sufficiently large compared to the degree d and the domain dimension m, we have an embedding of a projective Stiefel manifold that induces isomorphisms in a nice range. Now, this doesn't beat Mostovoy's result, which was one of the original intentions when I was trying to do this, was sort of see how these structures could tell us things about these spaces of maps. But it does give us a different sort of interpretation of what that space's cohomology actually looks like, where it's actually coming from. And moreover, if we switch this condition, if we let the degree now be very large instead of letting the target dimension be very large, we get an alternative statement on spaces of non-degenerate maps, right? And what I'd like to mention is sort of why this is interesting to me, why this is exciting. And it's motivated by point counts. This will just take a couple more minutes. So the basic idea here is that as the degree D grows, this statement, this inclusion of non-degenerate maps into the space of all maps really starts to carry more and more of the homological data in it. The way we're going to come to this is by looking at some statements about arithmetic. So I did promise you arithmetic at the start of the talk. So the sort of technical details that we'll just brush under the rug for now is that all the spectral sequences we're using here, all the maps we're using, are all the continuous maps that we're using are all algebraic, which means that they're going to respect the weights, they're going to respect the traces of Frobenius, they're going to respect all the things that we need to do our point counts, which means that we can, in some definition of easily compare topological data with point counts. So this embedding of a projective Stiefel manifold in the degree D morphisms from PM to PN, the fact that it induces isomorphisms in some range gives us a corresponding point count estimate. and it's this one. This one generalizes the m equal, or the m equals 1 case by Farb and Wolfson. I think I mentioned that here. Yeah, generalizes this sort of well-known count. And sort of the interesting thing is that I've like actually carried out this count for some degree equals 2 cases. I'm working on a degree 3 and 4 case now, and this is something I'm actually looking at with Nathan Kaplan in ongoing work, because like there's sort of reasons to think that maybe this count won't be correct, but like in all the cases we've examined so far, and in some particularly surprising examples where we're actually looking at these spaces in terms of some stratified vibrations, whether there's all these different sort of things that are happening. These counts have worked out to be so correct in every example we've checked so far, which doesn't prove that these homology, or that these maps are inducing isomorphisms on rational homology, but like at least it doesn't disprove it yet. It's interesting. In addition, this statements about building spaces from non-degenerate maps, in the cases of topology, we've got these spectral sequences where we're computing the space of the homology, the cohomology of the space of maps in terms of these spaces of non-degenerate maps. When we translate this over to arithmetic, it becomes much more about like inclusion exclusion arguments, and those arguments become a lot easier to do, at least in this particular case. I'm not going to like try to claim that number theory is easier than topology by any sort of stretch, but in this particular case, we can compute things about these spaces of non-degenerate maps. The easiest one is this one. This is just a point count, which just tells me like if I want to look at all the non-degenerate maps from P1 to Pn and see how many solutions to these equations there are over FQ, we get some nice form for it. And it's even nicer if we divide by the number of just all maps from P1 to Pn. We get this term. And this is telling me like the probability of a random map being non-degenerate. To which you say, okay, like who cares? Like we can't just take a statement like that and relate it to topology. And I say, actually, yes, we can, because all the maps involved are inducing isomorphisms in the right ranges. And we don't get like an exact, we get a prediction. We don't get like an actual theorem. So this point count, this density statement turns into a sort of density statement with respect to Poincare polynomials. So this point count, which is true, becomes this sort of conjecture on Poincare polynomials that relates the homology of non-degenerate maps to the homology of all maps, right? Or spaces that are in. And in particular, I realized this is something that I proved independently, but I also found it like in an old thesis of Crawford in 1993. If we look at the n equals 2 case, we find that this prediction, at least in the n equals 2 case, holds true, that the space of degree D maps from CP1 to CP2 that are non-degenerate look like the space of CP1 to CP2 maps of degree D, all of them, but also with this additional sort of thing that's behaving like a sphere, this like s to the 2d minus 3. So this is like an example of we get like these arithmetic counts and they predict something in topology. This is all I have. I haven't done any sort of cases higher than this, but it's like exciting that we can like draw these results from topology. This is the stuff that really like gets me out of bed every morning, that we can like pull these things out of number theory and connect them to topology and vice versa. I think that's, I think that's more or less the end of the talk. So I will just sort of summarize that we have, first off, I mean, uncovered this like bizarre phenomena regarding these like spaces of least degenerate maps, at least in the cases of CP1 to CPN and CPM to CPN. We also have developed this like spectral sequence that at least gives us some sort of quick and dirty like limiting statements for spaces and maps from X into CPN, because we were just relying on the stratifying by degeneracy in CPN. We also established some new type of limiting estimates for the homology of spaces of degree D maps from CPM to CPN. And last but not least, we've got some like topological predictions for subspaces of non-degenerate maps that are coming from arithmetic, which I just think is really cool. That's everything I've got. So thank you again to the organizers. Thank you to all of you for listening. What questions do you have?
Let's thank Claudio. Any questions or comments?
Oh, I've got bibliography.
I have a little question. So in a case of rational maps from CP1 to CP1, there is this point count for the moduli space of rational maps that has the same point count as the affine space for CP1 to CP1. Is there a higher dimensional analog of this?
I want to make sure I understand what you're. So what is this point count exactly? Was it on one of my slides, or is this a different one?
No, it's a different one. So the moduli space of rational maps has the is the quotient by the conjugation action.
Yes. Yes.
And-
Yes. Yes.
And that has interesting point count in the case of CP1 to CP1, which is the same as the affine space.
Yes. This is so. Sorry. Go on. Go on.
Yes. So the question is, what about CPN to CPN?
Right. So this is actually a really good question. Something that I don't know the answer to this question, but like I guess I can at least connect you to. So there's you probably have seen this paper, right? But there's this paper by oh gosh. Sorry, the name escaped me at the moment. I'll find them in a second. But there is a paper that looks at the sort of topological side of this. It's Maxime Bergeron and who else is on the paper? Let me really fast. It's like the topological aspects. Though I think you're also one of the authors of this paper, right?
Oh yeah, yes.
So it's not a useful thing to. Sorry, I just realized I was like, your name looks really familiar. So yeah, I don't know the answer to this question, and I guess the thing that's tough about it for me, that was really embarrassing. Sorry, but the precomposition action is, I mean, as you know, right, is like much more poorly behaved than like I mean, it has like much more aberrations than the post-composition action. I would love to like think about this question, but I don't have an answer for you off the top of my head.
I mean, it's about a point count story. I don't know much about it either, but it seems that it's very interesting that when you take the quotient by the conjugation action, the point count becomes much simpler. It becomes like affine.
Yes. Right. That's a good. Yeah. Let me. Maybe we should talk after, because I had some thoughts on this, but I think okay, we'll come back to that. But I don't know the answer to you now. And I agree that it's very interesting that like the counts become very, very simple.
Any other questions?
I think I asked you this over email, but I still think that
Yeah.
it's interesting to say with torsion, you know, compare all degrees at once, but you want to compare degrees that, you know, certain divisibility conditions, compatible with what coefficients you're looking at.
Yeah, and I do think I thought about this a little more. I don't have an answer to it yet, but like I think that we could actually get at this question a bit, at least in like some of the regimes where the degree is very large, or you know, like these sort of things, using some of these spectral sequences. I don't have an answer, but I also think this is like a really interesting question, and I appreciate you for forwarding on some literature on it, because I didn't like I wasn't aware of the scope of this work. But yeah, I'm sorry that again, my answer is I don't know, but it's a cool question.
If there are no more questions, we can thank Claudio again.
Thank you all very much. Thanks again for inviting me.